Get out of your head. Do this. You can do this. You can do this. Just. All right. So maybe it was confusing last time, and maybe it'll be more confusing this time. I'm trying the best I can. I apologize, but this stuff is just new. It's methods of finding velocity fields. And minor algebraic steps, minor things like that, they're hurdles along the way, but we have a lot of tools to help us do these things right now. But the most important things are just really assumptions on the equations we have. Assumptions give us simplifications, and those simplifications establish new differential equations. So everything that we're doing in this class is just that. It's just us formulating assumptions at some rigorized way to come up with a simpler set of equations to solve. All right, so last time we looked at this stream function, right? And this was a new way based on this Lagrangian of u. Okay, everything, this stream function just came from this idea that I'm going to say, all right, that fluid velocity is modeled by a bunch of independent paths, a bunch of curves living in some domain. And I don't know what the domain or how these curves are made of, but I'll say they're modeled by that. And you come up with a differential equation, right? You come up with a fourth order, right, PDE, for your psi. That's really what, right? Essentially, we did that, and you have some kinematic conditions to get you there, right? Prior to this, right, you really have Navier's. I mean, these things talk to each other. Okay? Before then, in terms of finding this came up with a second order system of PDEs, partial differential equations. So I should really specify here fourth order sort of one PDE for the stream function of x and y. You can do it for 3 dimensions as well, but that's the idea, right? The stream function and potential flows are different from this, and we're going to talk more about potential flows because they have more beautiful methods to solve things with them. That's a really big thing I would like to get across in this lecture, is just how if you do get this irrotational assumption pinned down, and you can say, yes, my flow is irrotational, you have a fantastically gorgeous method to calculate stuff. But everything's built up in you saying, my flow is irrotational. Seems like an arbitrary statement right there. So, and it is weird. You do have to say things about how the flow is working, but I think just a secular type of reasoning through these equations helps you rationalize that. So the biggest thing with the stream function is you had a fourth order PDE, singular PDE to find that stream function. We did x and y. It also could be of t. When we have the unsteady Bernoulli's equation for ideal flows. But stream functions, these things can handle viscous flow, importantly. Right? I can handle, right? Both of these things can handle a viscous flow. Right? Essentially looking at Lagrangian. I mean, these are initially were called like, it was called like the Lagrangian path function before. We called it stream functions. And the Navier-Stokes equations where these are layering things. And actually, I used facts of Navier-Stokes equations to inform arguments about the stream functions as well. Maybe you caught that. If you didn't, it doesn't matter. But like there is a circular sort of reasoning with these two different viewpoints, which makes sense because they're equivalent. You can start all of fluids with just thinking about these paths that are separated, and you can inform the derivation of Navier-Stokes. But it actually is it's far more difficult, even as how difficult it was to derive these things from fundamental principles of math, right? It's far harder, I think, to do it from the, like, it's a fiber bundle of a manifold. I mean, these terms get out of control after a while. So I think this one informing the stream function reasoning, right, is a bit cleaner. And if anyone wants to like self-study and see how the reverse goes, go ahead. I'm not going to test you at all on that. Go right ahead. If you have questions, I can tell you how that works. But I'm not focusing on that for the class. But I am really trying to get across, right, the purpose, the point, and the reason we do these things. Okay, I mean, right, and just holding it in your head, right, you're trying to figure out that's all we're trying to do. So how do we do that? There are methods that use these Navier-Stokes equations, or it's a system of PDEs. I've showed you scale arguments to simplify those PDEs, and that makes it a simpler PDE system, which we then use some other tricks of math or some other tricks of reasoning or scaling, I like to think of it as, to reduce PDEs to ODEs and solve that to figure out what these velocities are. But the other thing, the biggest thing about stream functions is it turns this problem sort of like flipping it on its head, right? Right? The act of a stream function or potential function is really just, right, figure out, right, figure out the psi, right, or a potential, and this is if. It's only if it's irrotational. Only, right? So this is a big specify. And I keep a different notation, right? I have psi for a stream function. Again, stream functions can handle viscous flow. I will test you on that. But your potential flows, your ideal flows, your inviscid flows, fundamentally can't handle any sort of viscous nature in there. Last time we solved a viscous asymptotic suction flow through two walls using a stream function. But the potential can't do that, because the idea of the potential function is that it's coming from the assumption that you have a curl-free velocity field, right? These are very subtle things, but they're very important, because if you know the assumptions, you then can do marks on paper or clicky-clacks on a keyboard and figure things out. But what really matters is what justifies these reasonings. But all today we're focused on this, right? This idea of if it's irrotational, I then have a potential flow. Right? I think of them as potential flows. They're called inviscid flows. They can be called ideal flows. However you want to label them, that's the point. So this lecture, we're only going to look now at this, if this assumption is satisfied. If your flow is irrotational, right, the analysis appropriate can be done with potential flows, ideal flows. And this calculus of methodology of finding then the u, v, and the w is like, you know, just magic, I think. It's just stupidly just like, it just seems too good to be true. And there's a little bit of strangeness in there because we'll talk about a complex function. But regardless of the method of math I'm going to use to like describe this, right? However I do that, who gives a hoot? The idea is there are tricks to get at this irrotational potential function. And if I solve it, I can then give you the u, the v, and the w. And then even better if I do that, similar with all incompressible flow. And then pressure comes from u, v, and w. Again, it's all 2D. So even for this ideal case, I will do 2D flows. Now we'll do the 2D flows because with the 2D flows, you get this complex number trick. It's also a good trick. I mean, it's also just, for the most part, 2D flows is a fairly good assumption. I mean, 2D flows even works if you have an axisymmetric case, for instance. I mean, what does 2D mean? Anyone? Anyone in the class? Anyone? No one's here. Right, so two-dimensional flow okay, so a two-dimensional flow means that like one, right, so that means that one dimension just doesn't matter, right? Right, that's the idea. A two-dimensional flow means I have three dimensions of space, and having a 2D flow means that one of them doesn't matter. And there's a couple ways that can happen, right? There's the slot flow. What does slot flow mean? That means we've always said like W, or the length scale of W, so capital Z, going to infinity. So there's no point, right? There's no actual change. There's no changes in there. Right, the other way I think 2D slot flow is, right, the velocity in there is 0. So there's no into the board or out of the board velocities we have to deal with in slot flows. Okay, this is one idea of having one dimension not matter. One of my momentum equations had no value. Right, 2D flow means that only two equations, right, say something meaningful. So in 2D flow, you'll have, right, if it's three equations from your vector equation, right, so you have some 1, 2. Essentially, what 2D really means is effectively one of the equations is just saying 0 equals 0. So it's a trivial type of equation to write down. But there's also one dimension not mattering. It also means that there's a symmetry involved in your problem. So one way is you have some symmetry about some axis, right? So cone flows, things like that. So in a radial type flow, it also means there's some symmetry. Now, how do you say there's some symmetry in a flow? Sorry, you got to say it. Right? It's no different than someone plugging around on a CFD code and saying, like, I'm going to say we're going to go axisymmetric on this boundary condition. Right? It manifests itself in a boundary condition, but this idea that there's some symmetry in the flow, this idea that one dimension has a symmetry about it, so I can throw it away. Okay? So 2D is not some super restrictive case, I think. Right? I mean, even approximately symmetric can get you kind of there, I think. You know, while most flows are all totally 3D, right, you could think of how, like, there's an approximate symmetry in one of the dimensions. So analytically, we could say 2D, and whatever is actually not symmetric is going to just be like a little tiny term that maybe doesn't really matter. So again, I'm doing potential flows. I'm also going to do potential flows. I'm only going to do 2D potential flows right now. 2D meaning two things. Either one dimension is infinitely long and far in the other. That means I have no scales and everything balances out. Or this idea of a symmetry in the flow. So symmetry meaning that there's like, if I have like a circular problem, right? A symmetry being, let's say, that if I were to look at the exact same velocity profile at this dimension, after I rotate an angle, they look the same. Right? So this and this would look the same. There's no swirl difference. However I orient myself at any angle in some radial flow going in and out of the board, right? There's a symmetry there, and you can utilize that. So that's one symmetry. So 2D is not really like the most restrictive case that you'll never use ever, and 2D is just an assumption that you educated people use all the time. I'm an engineer. I like to use the full 3D case all the time. Stupid. Okay? A lot of these things are totally okay to make these assumptions, and whatever your computer's doing, it's only going to calculate like a 0.4 difference, right? But you get paid enough, and that's enough how you can make your money, so that's fine. But even though you can show that some of these things are totally negligible, people still want to calculate them, I think. So after all that motivation that people, I don't know, maybe it's really just this to really start everything. If I can really define then when a fluid's irrotational, then I get my cool methods that I'm about to show you. So then let's start there, right? I talked about this before, this idea of irrotation, this idea that there's even very rotational type flows are in fact irrotational. I mean, irrotational is a statement about math, right? So clearly you could just have, so one definition of irrotation, right, is I have the curl of my vector field, which I don't know in the first place, equals 0. Right? So this is where I dig in these assumptions, because past these assumptions, which make simplified models, right, everything's ticks and tacks on paper and clicks and clacks on keyboards. So how do you really know that this is non-rotational? Right? I mean, it's just so arbitrary. But I'm trying. I'm making some type of physical argument, so you can kind of like, oh, okay, that makes kind of sense. So what did we know last time, though? If I did show this, though, so if this is true of my velocity field, if I'm somehow saying that my velocity field, my vector field, it's a vector field. If you go back to lecture 1s and 2s, right? Vector field. You give me an x, a y, and a t, a z, x, y, z, t, whatever. I will assign you a vector somewhere. So that's what this v means. It's a field. But this point that the curl of that, if that's equal to 0 identically, right, you then get this idea that if that's the case, well, my vector field, right, is the result of the gradient of a scale field. Okay? It doesn't go the other way. Just because you can't just write any function down, right? This is important, right? The converse is not true, right? I can't just write down a scalar function of x, y, z, and t, take the gradient, and find the velocity field of any flow. But what I do know, right, is that if I have irrotational flow, then this is true. Right? So the converse being, right, whatever, no one cares about converses. So just accept this, that if you can show this, that means I can find the velocity field by this kind of simpler thing, a scalar field. And then plugging this into continuity, you then find more things out about the phi. Okay? So just from here, you then go, well, my fluid flow has to satisfy a continuity type situation, which is coming from the Eulerian view. But I am promising you can go the other way. You can. But let's just say we're going to take everything learned of the Eulerian viewpoint of the Eulerian definition of conservation of mass. So then from here, you get this idea that, right, this, you get a sort of Laplacian of here. Okay, and this means something. This now means if my flow's irrotational, means there's no imbalance of shear forces on little elements of fluid, which is a physical interpretation of that. Okay? If I have that, that means that all the velocity field can be modeled then by this potential function. So now I'm on the hunt for the potential function. I don't know what the potential function is, but by continuity, I do know properties of the potential function. Any function I write down at least would have to satisfy continuity, right? Okay? So there's certainly some restricted class of these potential flows that I must have, right? Very importantly, I'll test you on this as well, right? Remember that psi, the stream function, automatically satisfied the continuity equation. It's not the case with phi. Okay, phi is my potential function, and it's just like too general. But what I do know about phi is I do know that it solves Laplace equations. And I also drop a lot of markers all the time. Okay, so this is what I know about phi. Psi is different. Psi I know. However I define psi, my little nabla dagger ensures that I will always satisfy continuity. Not the case with these potential flows, right? I mean, you could write down any function, right? And I can surely make this not be the case. So you can write down a phi, and this won't be the case. So so this idea of an irrotational flow, it's not guaranteed that any phi you write down will satisfy continuity. But it is guaranteed any phi you write down in the context of stream functions will satisfy continuity. I'll test you on that. So there's more on a hunt then for that potential function, what it really means. Where can I find it? Can I pin it down a bit better than I have before? But there's certainly good enough reasons to hunt for it. So how can I ensure that irrotational part of flow? So here's where I draw some pictures. It seems my second lecture, I feel at least, is better than my first lecture. And I apologize for that. Or they both suck, and I'm also sorry about that too. Okay, so here's this wing example you have, where here's a wing or a foil. It could be any really body, I don't really care. And you have, let's say, flow going in there. So just in general, right, if you made this experiment and then saw it happen before your very own eyes, you will clearly get the situation where, right, at some point, right, I could set some sort of parcel of fluid or some sort of bubble, let's say, and I would see it not really deform ever as it moves along its path. Okay? So again, here's some body. Imagine I've made some two-dimensional experimental thing. So that, let's say I have two plates of plexiglass, and I've made some obstruction in there. Right? And I have some bar that's releasing bubbles, and I have them move over my body as I have a constant pressure gradient across here to establish some type of flow. Again, realizing that pressure drives flow. There's no pressure. Okay, so this idea that there's, at some point I realize, I visually see that my elements of fluid or my bubbles don't seem to be rotating. Corners and bubbles are difficult, but you could impart a box of glycerin liquid that's immiscible, and you would see that same box of glycerin liquid be moved along if it was slow enough. Oh, I just touched my mic. But there's other parts of this flow too, right? There's this one part too, where if it goes in here, and you get this viscous interaction part. So this idea of boundary layers. We'll talk about boundary layers. Don't worry about that. But you have some sort of region where there's certainly no slip here. There's no slip happening here. There's no slip happening here. And there's some separation part that happens. And sort of maybe again here. This will happen much quicker, though. OK. Here's the body, right, that you have. Solid body. And then and then it's sort of in the behind of this situation, you have even this kind of part of flow occurring where these vortices. I don't really know what vortices are because I want to save that. Where the flow is swirling a lot in the background, and you just have these different regimes, right? So there are definitely, even in regimes, even in the most turbulent, right, sort of high-speed type of situation, you have some sort of body. You'll have some sort of viscous part of this flow where the viscous regions are important. Why are viscous regions important? Okay, this is where a boundary layer is, this is where the viscous part is. Okay. What is important about the viscous region of the flow, right? And I will test you on this. The importance of the viscous regime for even your highest level of flows, right? For even U infinity equaling 10 to the 81 meters per second. You certainly can. Actually, you can't have that velocity because of the speed of sound. How about just 10 to the 5? Work? No, it still doesn't work. Really high. We're not compressible in this class, so I don't want to go. Okay, so we'll just do that stupid limiting thing. But even if my velocity is extremely large, the important part about fluid dynamics is that you believe that no matter what, at the actual interaction between that fluid and the base of the solid, the velocity is 0. So there had to be some length scale such that even though this looks like an enormously fast flow, there is some level of distance. There is some minute, tiny amount of sub-nanometers that this has to become 0 at some point because I don't have slip at the surface. Okay? Right? So that is a physical thing, a physical assumption we make on these governing equations, right? You don't normally, for a governing PDE, you don't normally just say, like, I know a boundary condition. But Navier-Stokes, right? But fluid flow, you get a boundary condition. You hold on to that sucker as much as you can. And that is the no-slip. And that's why viscous regions exist. We'll later see that there has to be this other region where there is clearly right? There's clearly a rotational part in this part of this flow of these vortices where it's just totally where there is actual vortice or spin in the fluid, right? Curl is this idea of little elements of fluid spinning. So this is another region. But then there's still this region far, far away where I don't even see the body, right? The curl velocity field is basically 0. Again, maybe in this class you appreciate that we never say something really is 0 because 0 doesn't exist and infinity doesn't exist. But arbitrarily small, you can say this far field is actually curl free. So what involved in this is, like, let's say this Reynolds number, right? I can have some Reynolds number at this fixed velocity. Okay, this is a Reynolds number definition, right? So at the fixed velocity of this flow, I just have my velocity. Let's say it's 50,000 miles per hour. No, does that work? Let's say it's 800 miles per hour, which is now compressible. It's compressible around here, though. Right? This is moving pretty quickly, but if you move very far, far away, right? There is maybe a slight interpretation you have, which is the idea that, well, if I zoom very far away, right, I could still see some change of streamlines in my flow if I zoomed out far away enough. But in the sense that, like, all of those dynamics have been pushed down this very tiny little bit of the whole field. But they don't really play too much part of it, right? I mean, hopefully in the camera you can't actually see that little thing. Yeah, let's do a little dot, right? That's the important part, right? So if this flow exists on some, like, let's say, a length scale. What's the length scale? Well, I would say probably this length of the wing, right? So if I zoom into, like, I can kind of see the length of the wingspan of this airfoil. Then all these things are happening at the same time, and it's really rough. But then, like, if I now look at my flow field with a very, very large flow scale, we're now here, right? The velocity right here. I still have maybe this very fast-moving field. This is almost just a tiny little dot just zipping through fluid right now. Okay? You can do this experiment even, right? You could have a 2D flat plate of, like, glycerin, let's say, with a bunch of, like, magnetic particles or shiny bits of fluid in there, and just have the tip of a pen at the bottom of it, right? And then you just quickly move it through, even with a machine. Right? Because the pen tip is extremely tiny, right? You're not even really seeing any of these effects. Right? But as this pen tip gets larger and larger, let's say as the type of this body, then you'll see these magnetic, then you'd see these particles, these reflective particles start spinning at the edge. You'd see this like no slip regime as well because you're zooming in. But if you zoom far enough away, it kind of just has this smooth lines just kind of moving over themselves. And that's also kind of one way that irrotational flow is getting at. Okay, it's intuitive, right? These are just me drawing pictures that are just like describing the equations, which is, a contested thing. But it really is just that, me just describing how, like, what irrotational is me looking at, like, well, if it's a curl-free vector field, this is what the equations say. And then you go, like, how can I interpret what that equation says? So you can make up scenarios in your head. But then you also can do these experiments and, like, affirm that what you saw by the mathematics is right. And that's the point of theoretical physics, right? If you want to be experimentalist, then you still need to affirm something with your experiments, I think, right? Discovery experiments are nice, but it'd be nice if you could affirm something, or not, or you just experiment something and go don't know why this is happening. Also, really sweet. But classical mechanics is basically known, so that'd be really hard to do. Not to say it's not impossible, but especially in fluids, right? You can photograph and do a lot of cool experiments to say why is this happening? Okay, that's my little blurb on a way to maybe observe when a flow is irrotational. A flow is also irrotational, right? So flow is irrotational when? When is my flow irrotational? Well, I have a bunch of examples. One way is there's no net viscous shear forces. And this also relates to this curl property as well. Right? Curl talks about little bits of area with vectors out of them. Okay? Right, so graphically, right? This operation means graphically you have some sort of parallelogram area, okay? And that's what this is. That's this vector, right? That's emanating out of some tiny amount of area, arbitrary area, right? And it's telling you, right? The size of this vector tells you how much, right? This bit of area is spinning. Okay, so if this quantity okay, so if it's a very, very large value that this cross product is with this vector field cross product, that means that these little bits of area are whipping around really, really quickly, right? And the scale being the size of this vector. So large vectors out of little tiny bits of area correspond to extremely rotational flows where if I were to draw any little bit of surface area in my vector field, it would just have an enormously quick rotational velocity to it, right? So then small okay, so this is this large cross product with the V. I have a very large emanating vector field out of there. And if it's very, very small, it's just barely moving. So it's an interpretation of what this god-awful multivariable operation means. But importantly, you have to understand that it's talking about little bits of area. The gradient's not talking about little bits of area. The divergence does not talk about little bits of area. Cross product needs to have some amount of tiny area to say anything. So, right, the idea of no net viscous shear forces means there's no spinning happening, right? This is very small. Some other ones that kind of, right, there's some other ones that sort of are corollaries. We could say well, I'll just say that my viscosity is extremely small, right? So for, gas flows, I think like this is on the order of like 10 to the negative 5, right? Effectively 0. I'll roll with this methodology if that's the case. And there's another situation, right? It's another one, right? So you could also kind of get it, right, if you have, right, if very large length scales that are blowing up, right, you also could then write the Navier-Stokes non-dimensionally and then redefine that in terms of cross products. But as this blows up and there are no comparable obstructions around the flow, you could also maybe say irrotational flow. There are ways to kind of get around where irrotational flow is true when it's not flow. It's certainly true, right, that it's certainly true that if you have a gas flow where the viscosity is essentially 0, you have an irrotational flow. It doesn't have to be, right? But more so, this idea of no net viscous shear forces is very critical. Right? That's the biggest one to really show. But it's hard to say that because you need to know what the velocity profile is to then say that, right? I see I'm saying many circular things, but that's the basic thing about affirming this assumption that you believe that your flow is irrotational. But if there's no viscosity, then it certainly is irrotational. But you can have viscous flows that are irrotational. That's the vortex example. You can have a very strong vorticity happening, right, in a very viscous glycerin fluid, and you just whip that vorticity around, okay? And if you did, I said okay again. If you did that, you would still have an irrotational flow. And that's this idea that even though it's viscous, there's no net viscous shear forces on some element of area. And again, you show that through the cross product of V, right? It has to have reference to some amount of little tiny bits of area. This is sort of separate one where if your length scale is far away from any sort of viscous forces at all, well, they don't really matter. No, I'm just going to start fresh. So that's again, some more soapbox on the idea of affirming that your flow is irrotational. I gave you three different, let's say, examples that your flow could be irrotational that you would then assume. And it gets back to that far field flow that we talked about all the time, that we referenced. And this is a lecture where you'll see where I put those stupid formulas up. They were like, why'd you put that there, Sam? This is it. Before we get there, since we're in 2D, okay, I'm stressing everything I'm saying is about 2D flows only. And I don't want people coming at me saying not solving a problem, Sam. It's only 2D. Everything's 3D in real life. Not the case. You can always make some scale argument that one dimension doesn't matter. So it's still useful. I think it's useful. Anyway, back to 2D flows. We'll also go steady flows. And again, still general enough for a lot of flow problems, right? What does steady result in? What is the steady term? What is steady versus unsteady? So we've done enough problems today that you should realize that steady and unsteady is this idea that if it's unsteady flow, it means you have moving boundaries. Well, how often do you have moving boundaries? Sure, you could just say everything's unsteady and fully three-dimensional. I guess technically you're right. But it's not really right because unsteady flows need to have a moving boundary, which they can. But even if your boundary is moving, I can do a similarity solution and I can still get something out of it. That's the oscillating plate. So the unsteady term is in some sense only measuring like the impulse of some initial perturbation to your flow problem. So steady is also a very, very, very general type of assumption. So with these assumptions, now let's get into how we would do something. So let's have an addendum. First, complex numbers. If I have a 2D Cartesian plane, right? If I'm in 2D, here is my flow. It exists on the 2D Cartesian plane. Any point on the Cartesian plane, right? Some radius away, some angle, you could say vector-wise, and then you would have that r. Okay, these are just operations, and what does this rely on? It relies on the Pythagorean theorem. If you don't believe the Pythagorean theorem, it's rough, man. Okay, so this point also as well, let's call this a point P. The point P, which has x and y coordinates, can be represented by what? It represents by this r and this cosine. Okay, so this is the Cartesian life. This is the 2D plane. Any point in the plane, I can then speak of it this way. Okay, in the complex world, if we talk about complex numbers, so here I'll even call this axis the imaginary part of a complex number z. This one I'll call the real part of the complex number z. Right? Z is a complex number. Okay. This plane, so it's a two-dimensional plane and a two-dimensional plane of numbers, this plane also has relationships. So here is just my point z. It is a complex number. It has some, right? It has something called a modulus, same sort of relationship right there, and then it still could have some angle theta. A lot of similarities going on right now. The only big one I want to get across to you is the fact that like this point P involves two different things I track at the same time. But in the complex world, it is one thing. It is one object called z. Cartesian, I've broken up into these two parts. I got an r and a z and a sine and theta. But you have to appreciate with complex numbers, it isn't two numbers. Now, you can have this representation that I'll say it's a real number plus the imaginary number plus some other real number y. That's up to you. But it doesn't mean that the complex number really is two things. This is a representation of it. And then similarly, right, I could also represent this in the case of a radius, the exponential, and then I e pi, right? So these connections are very critical for complex numbers. The fact that this number is these two parts. If I want to go to polar coordinates where I have some radius r, I could also express the same complex number in a different way using these coordinates right here. Right? Recall this uses the most magical equation ever. Okay, where this definition applies to this. It's a natural analog to the Cartesian plane. I could go on for 8 hours on complex numbers. They are absolutely the most magical things about all of math. I think they're under-taught. I think people should appreciate them more. Fortunately, I'm not teaching a complex analysis class, which sucks. But this is an amazing thing to show you how it seems like cheating if you use them. So the idea these are complex numbers. They have these representations. The idea that there is something there. So for an ideal flow, the idea, right, ideal flows, we already sort of stated the idea that for an ideal flow, inviscid flow, potential flow, however you want to say it, right, the idea is that the velocity field is the result of the gradient of a potential function. This is a real value potential function in this formulation. There's a much overarching It's a very larger trick, and that's the idea if we look for a complex potential. Okay, where this is a function of a complex variable z. This is what z is. It exists in the complex plane, right? And I look for a complex potential here, where the real part is my velocity potential. The stream function then is added on. It's this part right here. So if you go then to me going like, hey, you said stream functions, talk about viscous parts. That's fine, right? The idea is this can also handle inviscid flows. It just can't do the reverse. So like this, the psi can encapsulate inviscid flows and viscous flows. This can't. So the phi is the inviscid part, but this stream function of the inviscid thing is also well defined, and I get it as well. So don't think that psi is only for viscous flows. It certainly isn't. But the fact that this is OK to do. Now, why you would do this, I will skip. But there are some reasons to do it, right? And it goes into the Cauchy-Riemann equations of how complex functions work and how they work naturally. Okay, essentially what happens is I know that this has to obey, right? I know that this has to obey this value based on the assumptions I have. And then the same thing, I have this equation also satisfying continuity. So it comes from this representation. I would say that my complex potential is the summation of the velocity potential, and now this stream function. And the idea that I have this one I know solves the Laplacian, and then this one as well, do the conservation of mass, solves the Laplacian. Okay? But we don't need to really go into that. The more beautiful part about this stuff, I think, is like just seeing how we really flip everything. And flip, you'll see coming up soon. So here's a complex potential, right? So then a complex velocity. Here's a complex velocity. Okay, this is defined by these equations. And they're symmetric, meaning you can pick whatever one makes it easier for you. Right? So this symmetry of these two definitions is what you get from this definition here. It's a motivation even for why you would claim that your complex potential has this form. And that's this relationship right here. So what's important is while I have x's on the bottoms of derivatives, I have a swap, right? Right? I have this swap of the phi and the psi. So the structure of complex numbers gives me this negative sign, and it gives me this x and y relationship. So all that's coming from this beautiful construction right here of what you would call your complex potential. Don't gotta get into it, because 3 of you care at this point. But we'll get to an amazing type of calculation, a calculus of getting velocity fields. So this is gonna call, right, this is a WZ. Derivative of a complex function gives me a new function. I'll call it W as of Z. This, just by the definitions of these bad boys, has this interpretation. This is in Cartesian. If I was in radial, I would have then this interpretation. Here. So I just had equals, but I'll have equals with an addendum in there, right? So my complex potential, this if Cartesian coordinates, and this for polar coordinates. But I leave the equal signs in there because people should appreciate now, regardless of your coordinates you decide to choose as some measly human, it doesn't care. The velocity doesn't really matter. It's just a representation problem you're having then. So there's algebraic rules then about these, right? So the q is a generalized velocity, right? And that's just going to be, right, a u squared v squared, still your Pythagorean theorem. Then your alpha is also going to be some angle. A positive alpha or negative alpha? Yes. So this wz is what's sort of the harder part because you have to think about a plane mapping to a different plane. So I don't get a three-dimensional view, right? I get this trick that with complex numbers and failing markers that are losing their ink power, here's x, here's y in my Cartesian plane, let's say, and flow is existing in here, right? There's the flow, right? The flow of a path that's going to be happening, right? And even in my Cartesian plane, I could represent this then in the complex plane. What does that mean? Well, I'll say that this is really an I, y, and this is my x variable, right? So my real part, right, and my imaginary part. I still have this angle, I still have this radius, and flow is occurring here. So importantly, the idea that flow happening here in this plane. The idea of this velocity potential giving you the wz transforms you to a different plane. Okay, where my axes are now u's and v's. Just negative alpha. Okay, here's my negative alpha now, and here would be my q. Yes, the q, obviously. Here's this q, the q being this just new radius I have. Okay, here's this point right there. So then this being negative v. That's my u. Okay. So this is what this wz represents, and that's hard to wrap your brain around it, but it gives you amazing algebraic properties to trick hard stuff, right? Okay, the wz maps from this plane where flow actually happens to my w plane. Right? So where flow's happening in this two-dimensional area, you give me a point there, I'll take that entire plane, map it here, and I can tell you where all vectors lie of velocity. They're just oriented to the base 0 right here. So you could put the velocity vector right here, right? What the w function does is it orients the origin of this coordinate system to this point right here, and then tells you how large and what angle this vector is at, or this arrow. So that's what w is doing. And these are interpretations based off of after what the math tells you. The other issue about this idea, if I said to always interpret complex numbers as complex numbers themselves, which is hard to do. But the other interpretation of this is q. What it really is the square root of the complex number that it's evaluated right here, right, times the conjugate. I'm really just getting to math right now, but it seems everyone wants to have like specific steps written out. So if this is a complex number, if this is evaluated to some number, let's say complex, an a and b, if I'm defining these complex numbers, you give me a complex number, and I will spit out some complex number, a plus b. Well, the conjugate of a complex number is what? It's a minus b. So you can see right here that that's the same thing as this, right? So, right, these definitions of conjugation of complex variables gives you this, right? And it's symmetric as well, too, right? I think this is a waste of time for a fluids class, by the way. I don't like doing this. Okay, but then the definition of this guy, right, gives you exactly what you're looking for. Right, same thing here. You can just use the same thing with a's and b's, but use the u's in there as well. So then q really is actually this idea of I take the complex number, and then multiply it by its complex conjugate, take the square root of that, always a real number, etc. So more of a complex thing. So I certainly have a good mapping of this idea of then looking for complex potential functions. There's just f's of z. And then if I have an f of z, I can get velocities. So now it's time to do one. Write down any analytic f you want. Take the derivative, and you'll get velocities and potential information from there. Amazing, magical complex numbers in action. So what do we have here? Which one did I do first? What does this look like? I'm just going to write out a complex potential now. Okay? Sort of f is a function of I, a complex number I, scaling up just the complex number squared. It seems reversed, but it also does really help that you get two things for one with this idea, right? So then you have a z, x plus I, y, x plus I, y, right? Put these together, right? Foiling things out for you. Then you break this up now into the imaginary and the real parts. Yes. Minus. Okay. Now you can identify what the potential functions are. Your velocity potential and your stream function even will come from this. More importantly as well, this is what we care about, the df dz, right? What do you get when you get df dz? Well, everything works the same. Just get to iz. That still works the same way, by the way, if it's analytic. So now look at this. Pretty neat. I wouldn't care about what, this idea of, it seems a bit roundabout, but the idea of like you can just say any function of a complex number. You can just write down any f you want, right? That's at least analytic, doesn't really matter, that definition really, anything you could come up with in your head, I would say, is actually going to satisfy this, unless you're really tricky and do piecewise stuff or shit like that. But I don't think any of you would even care enough to write that out. If you do, then like you're a beast. But like most things you can write down in this case of having z's in them, you write out the f, take a derivative, and then you can identify what your u and your v is. You can even identify what your phi and psi are, right? Even on this case, right, you have that Right? You can even identify what the potential function is and what the stream function is for these flows with just writing down something that comes into your head in terms of an f and of a z. Amazing, I think. Let's keep going. So let's then look at more of these FZs that I could write down. Let's look at this one. So let's then just look at, let's say, some real number, some far field velocity, right, alpha. So some number here, and I'll just multiply it by a z, right? So, right, I'm just, again, even here, I did one thing. What did I do? People didn't really care about it. I just showed you the algebraic rules of doing this. I have an FC. I write down whatever pops into my brain about some complex potential. It's a squared in that case. The idea of the W function mapping a plane to a plane, it's all in there. It's all in there. But let's dig in now. Let's just write down some F's and see what they do. This one's pretty cool. So now the W here, complex potential, complex velocity function from the derivative, right? Well, go ahead and do that. So you plug it in whatever you want. And then this interpretation, then remember, is this. Now, this idea of the actual df dz equaling this comes from a different perspective of the Cauchy-Riemann equations, but do we care about those? If someone does, Slack me, email me, yell at me, go for it. So do you stop here? Do you go like, all right, I took an f, took a derivative, am I done now? Well, no, because you can go backwards to the fz, right to the Cartesian plane and see what this is actually modeling. Right? So then with this case, if this is your, right, this is this very simple flow, but still all coming from your f you wrote down. So what this is modeling, what it ends up you modeled from posing this f, and again, don't get mad about this like, well, how the frick would I understand to write down to f? Doesn't matter. Just write down as many as you want and see what they model. So, right, this f, this complex potential is modeling this 2D flow plane of constant velocity impinging over the negative x-axis, angle alpha, and a velocity of u infinity. Not the most crazy flow, but we're certainly getting somewhere. I certainly wrote down something I could then do computations with. And I get like, all right, so I orient my axis some way, and I have this idea of flow going constantly in one direction at an axis alpha of x I choose. You're getting an entire velocity field for not much work at all. This doesn't end there, though. This goes deeper and deeper, I think. Right? How about another one? Pops into our head at one point. Well, I know how to do product rule, right? I took calculus, and then, I can handle this one. Okay, so a z to the n, right? If you take calculus as all, you go like, well, I know z, I'm worried about treating complex numbers like that, but you at least can write this out. You ask like Euler and people like that in Cauchy, like, can I take because of the same rules? Is the same rules. Okay, so the derivative of this is what? Okay, I don't really, this step from here to here, right? Just same as same as that power rule you learned at one point. Don't really worry about if you know like conditions such that it is the case, but for fluids, always going to be the case. Okay, I don't quite know what this is, and certainly powers are tricky. But when it comes to a power, right, with complex numbers, if you have powers involved, clearly polar notation is always better. Remember how z could equal some, right? Remember how z could equal some r? Right? This is the idea of a polar notation or polar representation of a complex number. So if you have powers, you probably can see how this is an easier form to work with them, right? So z to the n, I'll have r to the n. But then the power here, I just then get the I n, theta. I don't get any weird sort of like, it's certainly easier than like an x plus iy to an n. What, are you going to run the binomial formula on that and get analysis out of that? Pfft, good luck. So polar with powers is a very clear notation of why you'd want to switch to that form of the problem. So you get this w, but we're going to go like I'm going to go velocities on here. I'm going to go polar velocity on here, and then you get and then this, more calculations. I'm doing calculations on boards now because I don't know, people don't want to just do it in Mathematica. It's fine. So then you have n. Man, I just do this stuff in Mathematica. All right. So this is just me, right? This is just me carrying out this multiplication using Euler's definition. And then there's maybe one exercise in complex numbers, which is like not the worst, right? Is to show me that the w in the complex form using a change of variables means that this is the velocity Okay, this is one extra credit, I think. Just do the change of variables and show me that how velocity, if I change to a polar notation and I have coordinate transformations, how now the df dz looks like this, where I have really the same formula, right? Remember, right? I mean, this really is identical to this u minus the I other velocity. The fact that I just need to get this form where I have this e to the negative I theta in there hanging out at the other end. Why do you have it look like that? And then look what you have right here, right? So now you can just identify then exact velocities of what you want. So then, right, in this idea of flow, you then can say, all right, so that fz, it seems like, is modeling this NAR cosine n theta, okay? Everything I've done is just said, hey, how about this f? Who is it? Zine. I'll get back to you later, Zine. Can't. Get back to you later, Zine. I'm in the middle of something. So that's what these VRs and V thetas are modeling right now. Okay, so what do they mean? Well, here's where I really encourage people. I've mentioned Desmos on the website. I mentioned all this stuff about really just like, okay, you get some conclusions, and I'll start plotting them. Okay, also on top of this, right, before I took the derivative, you can also show, right, that the potential function would be this. And then my stream function is the sine part. And the n's in there. Notice the n's in there. The n's a parameter on my assumption of what the f looked like. So n's an independent variable, right? I give me a complex potential n. It's as a function of n. So where are stagnation points? Right? Stagnation points are where the stream function has to equal 0. Why does the stream function have to equal 0? No tangent divide. No tangent defined there. So if my velocity of stream function is 0 there, I get rid of that part. All good. Okay? So you look for a dead marker that doesn't have any ink in it anymore. So we have I, this idea that you have a stream function. When that's equal to 0, that's stagnation points. Last lecture motivated this because I said there's no chance to define it there. If we want to have a consistent theory, it means my stream function has to be 0 there. Well, that's the way it's going to work. Well, in this flow, you can solve for that. Okay, so this will always be 0 for this situation of a k now. So now I introduce a new parameter. I can have an n, but now for any n, I now have this like auxiliary k variable happening. So for any n I pick, right, I'll have this k, because n's just a number, right? But if this number right here is of a k pi over 2, right, n's an integer, so then this will still be 0. So n has to be an integer, by the way. So stagnation, where this is true for all values of r on the x-axis or the y-axis. So that is modeling then where the stagnation points on this type of flow are occurring. But you get a little more. You also see an issue of how the radial velocity at these points has a direction associated to it, like this. Right? These are just calculations based on these things. I mean, what am I doing right here? Yeah, so right, this VR, if I have theta equaling to this, right, I hope you're all comfortable seeing that how cosine of n times this, if n's an integer and this is k, that's just -1 flipping every kth power. If you don't comfortable with that, you just plug that into something and it'll show you that. So that's now my VR. VR, like an Oculus Rift or something like that. I played Beat Saber. It's so fun. Right, so what does this look like? Well, again, I highly encourage you to start plotting these things in Desmos or something, because you can get a feel then that way for how the flow's going. You certainly can't get it any other way if you're in this ideal case, for Christ's sake. I mean, I already said, like, flow's complex and I have a complex potential. What do you, but you can see then, if you like go, okay, what does this look like? Here's the situation you have. Okay, if this is k equal 1, n equal 1, right? So that means this angle is a pi over 2. Here's the stagnation right here's like this, and I have this must be equal to 0 on here. But I have a radial velocity now, which is equal to what's written down there. The radial right here, right, k is equal to 1 for this one case here. So this is where k is equal to 1. Go click up 1. That's where the k is clicking off. K is clicking around these angles right here. So that means the direction's now here. Here, k is equal to 0. So that means the direction is right. Any number to the 0th power is just 1. I have n, and none of these things are negative besides the a. If you flip the a, all this would be reversed. Say a is positive. So that's some angle right here. And then if you then plot your potential functions, right, this bad boy, you then see what's it looking like? Well, it's looking like some sort of a corner flow, right? Or for values of the stream function, right? Remember, what is a stream function? Stream function is a friggin' path that a fluid moved along, right? And it's defined by that function equal to a constant. So if you give me the stream function and set it equal to a constant, I will define one path, and that's a path where some element of fluid moves along. Whee, whee, whee. That's what they are. So a stream function set to a constant. These constants are not the same thing. They're different constants. They define paths of fluid. And you're getting the situation of some type of corner flow of a pi over 2. It doesn't end there. The beauty does not stop. Here is what's super cool. Now, how about n equal 2. So remember, the f was defined in terms of an n, so I'll have the same f. I'll make it 2. That's that pi. What does it look like? Should look pretty friggin' familiar. Boom. You recognize that? If you don't recognize that, I won't remind you. But this is this idea, right? If you calculate these velocities and then conform them back to Cartesian, you will get that Hemines far-field flow that I talked about. That's the n over 2 case. Oh, it doesn't stop there, though, with this solution. You better believe it. There's even stranger ones. You can have a plane, right? What is this? This is n a half. Right? So if you go back to what f was said, this would be a half. What do you get? You get this directional thing, the direction only specified by the constant a. Right? Right? That constant a that popped up in here, this is what's defining the direction now. So I could have essentially all these flows just reversing direction based on my a, but I have control over that. That's my power. You think I'm done? I'm not done with this solution, right? This even models, right, if I take different situations of something like flow over a hill like that. This is for when looks like that. Now that flow is looking like that. The magnitude and speed of these flows is governed as well by the a's that are involved. So think of a as actually your scale that you're just picking. If you just know the flow field is about 20 meters per second or 10 meters per second, just plug that in for a. The real dynamics now geometrically are governed by the solution. I find it if someone's not amazed by this stuff working and modeling a fluid, then maybe I don't know. I just think this stuff is crazy because all I've done is I just say here's my complex potential. And yes, it seems arbitrary, but all I did was I wonder what my power law looks like. Can I compute power law? You do it and you get all of these potential flows. That physically they govern so much that we seem to feel in real life. This one is for, again, remember where n was held, right? So if my n variable is, I let it be continuous, right? And within the integer, within integer fractions, if I make it to be a quotient. Okay, so maybe a quotient. You get the situation of flow going over this and over this. Again, remember, the direction is only determined now by this constant a, which is your scale velocity. And even one more that it can satisfy. Even the situation of flow over some sort of sharp point. That's what this is doing. Where this has some angle. Over an n? Yes, over an n. And this situation being only for strictly. Do you see those strictly inequalities? Yes. Importantly, this situation is for when the n variable is strictly between 1 and 2 as a fraction, but now you have this flow over a wedge flow, still modeled by this 1 fz. I just wrote down fz, took a stupid derivative, and you just get everything from that, right? And what I mean by everything is I have fully characterized the radial and spin and swirl velocities just from writing down fz, like magical. I can't seem to make anyone appreciate how magical this stuff is ever. I hope they do. It seems like a lost art. Certainly people don't care about it anymore, it seems like, because this is what people like Lagrange and these old mathematicians did, because they didn't have computers. They didn't have computers to just like solve flow over a wedge. And wow, I'm not some old guy yelling, going like, computers are stupid. They help a lot. But in terms of rationale, I think they're absolute garbage. I've never met someone that's really good at they throw away all type of intuition of what's going to happen with the solution with your computer. And why is it? I've said this many times in this class, a computer you have to run from an initial condition and just have it run. Maybe you have some uneducated like theory or conjecture from your runs you did, but someone else can come along and set some new thing and go like, you didn't know that. You can't do that with these math people, right? Everything they say is going to be right because of the assumptions they made. All right, now I can get attacked and slaughtered by the YouTube community, by CFD people. Okay, so now let's do another one. No one thinks this is amazing? I think this is just stupid. Okay, it doesn't really matter. It doesn't even matter that I'm just writing these down. So how about this one, right? So now here's another complex potential. Fz equals this, integer m, let's call it a real number, divided by 2 pi. This 2 pi is motivated by something called complex analysis and residue theorem, doesn't really matter, and then some natural log. So how about natural log complex potential? What does that look like? Okay, so from here, we have 2 pi. Oh, I wanted to talk about, So here is this idea of, so reference point, make it 0 actually. If I go to a radial situation here, right? So this z naught here is really just for, it's just a scale, right? If you remember that the difference that you could move this anywhere and you would just be shifting something. Or you could actually convert both of them, and it would just be a shift by an angle or a phase. I don't want to do that, but mostly this is an amazing thing, right? So then I have m over 2 pi, and then just carrying this out. I then have n natural log of the radius plus that. Okay, all I've done is just natural log rules. But this property itself is like one of the most glorified properties and explanations of this multi-valuedness of a logarithm, or this multi-valuedness of spinning around and always reaching yourself again. This idea that the polar form has this argument. I don't need to talk about that, but people, this is sometimes called the magic of complex numbers, that how my complex number in this form breaks off the distance and then this argument or spiral argument of a complex number. So it's sometimes called the magic of complex numbers that it does this. This is fundamental to like spin in quantum mechanics. It's really based off these tricks of complex numbers. Actually, spin's a property of the dynamics happening on a compact surface. Say. Okay, sorry. Okay, so the idea is in this form then, right? Because of how I defined what fz has to be, you then get your potential functions, right? So I have this r. I only broke this up because now I can identify these functions, right? So here's the velocity potential, and here's my stream function for inviscid flow. So the velocity potential has a natural log term in there of the radius or distance away from the flow you're happening at, and then stream functions are really only a function of this angular argument. So it's a very critical type of thing that in this potential type of flow, you notice that how the stream function only cares about like where your orientation is to some type of axis, whereas the velocity potential cares about how far away you are from something. All these things become evident once you actually plot the crap. But we're not there yet, so the idea is like, okay, that's my W, so then, right, again, it's just the definition, right? Again, I am just saying, you take one derivative of whatever the heck you want to write for f, right? You take one derivative, and then you get the w, which tells you everything about your velocity field, given it's irrotational. No? No one? Okay. W df dz, same definition I have for the w right here. I psi x. You could use the other one. They are equivalent. Any one of these examples, do that calculation. You'll see they are equivalent. Okay? So same thing here. And then I get identification. Really, a formula shows me. Are you ready? Are you ready? This is cool. There it is. Kinda. Similar. It kind of looks like the vortice flow, doesn't it? I tricked you, though. See how it's a radial velocity as a function of r. So this is not actually, this potential we wrote down is not the vortice flow we saw, where I showed you this 1 over r relationship. Not this one. This is a source and sink. Okay, that's what I'm talking about with this velocity potential, right? The idea of velocity potential, it's pretty stupid, but like with this idea, right, where really the sign of m now tells you in or out, so it's really a charge type thing too. So you see a lot of connections, right? So this is if m is negative, and then have some point source. That being if m is positive. So source C is a sinker source being only determined by this m variable in front, but the dynamics are captured in this natural log of a complex number. There are issues, though, with this trick. Okay, there are very unphysical issues with this trick that we should point out. It seems like a magic bullet that you can just write down any ideal flow thing. But there is an issue coming about singularities in these types of flows, this one being the most obvious. What do we have here? Yes. Yes. Okay, so in this one, the situation being, right, that when r equals 0 for the source or sink, I have an infinite velocity. Right? Even the vector, let's say, would blow up to infinity. Even the same case for my corner, right? Even in this case, right, where I had this situation right here, even at this point, right? So, right, even right here, still got a singularity in these types of flows. It doesn't even end there, actually, because these don't even satisfy conservation of mass. And you should maybe don't think immediately going like, wait a minute, I thought you said stream functions always satisfy conservation of mass. Yes, they do, but I did not mention, right, that is not the case for this type of potential, right? Because the velocity potential involved in there. We did not say velocity potentials always satisfy continuity, right? We just know they satisfy the Laplace equations. Very different. Okay, so for some of these flows that we're talking about, they will produce these velocity potentials that do not satisfy continuity. Okay, take this m over 2 pi thing I have here. Okay, so looking at the flow rate, what's my calculation? I multiply by an L because that would be the other dimension. Integrate from 0 to 2 pi. Essentially, I integrate over the whole thing. So here's, if I go here is 0, and I integrate all the way around to 2 pi. So that's my integral. What do I have? Well, I need to have the velocities, and that's all that's left over is this 2 pi and r. And then I have an r dr. Right, so there's the r, no d theta. Yes, d theta. Okay, right. Remember, this is your change of variables if you're going from a rotational integration, or right. Someone remembers that. If they don't. What do you get? Right? So then this, the d theta, becomes 2 pi. These cancel out. certainly not 0. Okay? And the problem with that, you can see right from there, right, this is really a velocity over a surface, where I have my surface right here. Right, so this integral right here is a surface velocity of, here's my sink. Here's the L. What I've done is I've integrated from this surface. That's what this integral is right here. Notice the flow rate out of the surface or into the surface, right? Flow rate out or in, right? It's this calculation right here. The L is just this integration up and down, but it's not different. But this flow rate is really this V across the surface. Now, divergence theorem says I can transform that to this, and what you have is this issue where now right? And this is just a sink or source flow. So ideal vortices even, I haven't done the vortices yet, but that's the thing. These ideal flows, they don't even satisfy continuity at certain points. It's sort of a troublesome statement because it's not like they're just like terrible. It's just the fact is like when you get close to these singularities, that error of continuity starts to blow up and it really dominates the whole velocity field. So don't throw all this crap away, right? I'm just saying, just be cognizant that these are very bad at approximating when you get close to singularities. We saw that. We saw that this can obey no slip, the vortice flow. And we have adjusted that through an asymptotically massive solution. You do that because right, the closer you get to that singularity, the more this becomes not 0. So now I need equations that obey the continuity assumption. So far, far away, this could really look like an epsilon. But as I get closer and closer, right, now this divergence starts to look like a positive number even. Bad. Even a negative number. Again, realize that m is just either a source where I'm measuring flow moving out of my surface or a sink where I'm moving it into the surface. But as I get close to singularity, I need to change my viewpoint and do that sort of switch to an asymptotic, uniformly valid solution. Okay, I'm not done. Let's do another one. Here's the FC, and now this will be negative I, some constant. We call it capital gamma, just because of circulation theory. All right. And then from here, I'm not even going to do it anymore. Here's really what we've been seeing all this time. Right? I've done this example multiple times where I said, in an ideal vortice, the swirl velocity looks like this. I say that because I'm modeling the far, far away field flow velocity as ideal. And I'm doing that because I'm motivated the idea that it's irrotational based on a shear argument. If I take a shear closer to the radius and outside the radius, if radius is pretty very far away, it doesn't really matter. So that's where this is coming from. Now, in circulation theory, this actual gamma has a definition as well, where it's the closed integral surface of my velocity, tangent vector, and then a ds. So this is arbitrary as well. So this value of gamma, which we will talk about extensively when we talk about vorticity, because the idea is this number becomes important. You can track the capital gamma as a function of time throughout flow in this interpretation. But for now, we'll just talk about the idea. Remember, there's this curl and stuff like this. If I look down in my vorticity, right, so here's the singularity point, right, and I just have right, just swirling flow, so this is a vortice. Vortex. It's a vortex. This is a vortex, right? This statement of gamma is actually independent of how I drew my path, right? There's a big thing that is, I think it's next lecture, yeah, where if I draw any path, let's call it C, right? Then gamma, it's an independent variable because it didn't matter how I drew my path. Any closed curve integral where I calculate this curve, right, calculate the integral around this curve of some velocity field, right, dotted with the tangent vector to this curve, right, times a little bit of space. So again, at every one of these curves, here is my tangent vector. So you define this integral you're doing. The idea being this integral of any curve you want to define, right, as long as it's closed, gives you one number, and that's this gamma. One number. It didn't matter how you calculate out that gate, right? It doesn't matter what the z is. So that's a powerful thing. We'll maybe talk about that more, about why that is. It seems astounding to me that that is the case, but it's a fundamental thing about this capital gamma. Okay, those are a couple, right? Amazingly, I talked about a vortex, I talked about a sink or a source, and these are the classic examples as well. I personally like to do this and just write down whatever the heck I'm thinking about for f, right? And then what I do is I like to take the derivatives, I like to see what it might be modeling. Sometimes it's garbage, sometimes it's something neat. But people have done a lot of these already, so kind of all the big ones are kind of found, I'd say. And really, they're kind of found because, right, the idea is that potential flows add. That's the cool thing, right? Potential flows add up to new potential flows based on the linearity of what we've defined and everything is. So, right, if I take a bunch of different f of z's, add them up, new potential. So here is leading up to my final example, getting closer to this f of z. I'll now define this thing. So u here Okay, so what is this? This is, as we've already interpreted, this is going to be that plug flow, steady flow with alpha equal to 0. What's this? Source or sink? It's going to be a source. It's a source flow at z equals 0, being ideal. This accompanying the idea that there was a z naught in there. You break it off, you have this I of c, right, this I here, and then you are allowed to, right, you break it off, you can just move the z naught wherever you want it to be in this flow we're going to talk about. Let's breeze through some of these things. Okay, so right here, what's the velocity field then? Well, again, it's just df dz. Z, forgot about that z. Remember, I had an exponential with an alpha in there. The idea is when the alpha is 0, it just becomes a 1 number. So that z had to be there. Okay, just one derivative. Now you get that. So as a whole, the complex velocity potential right there. Where are stagnation points in this bad boy? Again, stagnation points is when everything's equal to 0. What does that mean? That means that this expression, right? Because z is equal to, right, that. So then for this to be 0, right, I can move this and solve for these points x and y in the complex or Cartesian plane. If I do that, I can now solve for where the stagnation is occurring. Now what's going on right now, we can see a bit late. I can write it down now. Got my pencil. Oh, yes. Next thing, what's that streamline function? When that's equal to 0, I can categorize all these things. That's the angle. So when this streamline is equal to 0, that's points on the surface that would have, when this is equal to 0, those are surface points. So that is going to be, we can figure out what that C was, the I. This infers that. Right? Where am I? Yes. Did I do this? Did I do this right? Sorry. One sec. Yes. So here's this f of z. Okay? So then if I'm looking to break this up, you have the stream function based on how f is defined needs to be u in the y direction plus the angle plus this c. Sorry if I should have put that up further. Right. Just looking at this f of z term is the idea where, remember how if I make z polar, then I get the magic group of complex numbers where I just have this theta in front. Same thing with this ui, right? If I have this complex number, I'd have an I in it. If I'd have u infinity. Right. Importantly, right, everything with the I in front of it ends up being a stream function. So from this, here's the stream function. When it's 0, that means that this has to be, that means that this has to hold. That has to hold right there. So this is true then. And now we can start writing, like, sort of plotting some things, right? So now I have kind of a smoothish blunt body like this. This is going to be my R. Here is that theta, which corresponds to right there. Again, I'm only getting this stuff from just like plotting my weird complex stuff and seeing what it really looks like. Okay, so stream function equals 0 to all of these points right here. And then I'll have this other angle I'll call gamma. Everything work. And now I can also define now this constant h. Notice how ys can get smaller and smaller as I go further and further down, but eventually it will actually level off to some constant value. So this is h, and this is h as well. And you can figure out what that h is by what. Okay, so if I have the y is going to be equal to my m 2 pi u. This is a pi minus theta. Pi minus theta, that's this gamma term right there, right? So then as this goes further and further away, what do you notice? Well, you notice this turns, right, gamma turns into pi, right? No, this goes to 0, boom, 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 and then you get that h is equal to, right? So I have a model based on this potential flow of a blunt body moving in plug flow. That really should seem trickery and magic to you, right? I've just written down an fz. I took my velocity profile right here, looked at the stream function. Stream functions have to be 0 on the surface of some things because there's no tangent defines right here. So here's a boop, boop. All these points are 0. I really hope I am recording. I am. Right? Solving for when this is 0, I get these points x. So here's the point right here. Here's the tip. Right? So the body itself is encapsulated within this fz. Notice I can define where the tip of this blunt body is now by my scale velocity u. As u gets much and much bigger, this is shrinking down further and further and further. Right? As u becomes very, very small, I'm getting a weird thing that's happening. Right now, this is blowing up all the way. I'm just getting flow over 2 flat plates. Strange. You don't want to make this go to absolute 0 because why? Well, because ideal flows, right, are trying to model when viscous effects aren't that important. So when your u is really, really small, your Reynolds number is going to be small. This is a terrible way to approximate it. So it should be pretty high. It should not blow up. That's the point. And then m's going to just depend. M's only going to just make the direction of this blunt body work. And then you have this height of the blunt body you're trying to model as well, dependent on my m and my u. So if I have some desired h I want to model with my front of the plane wing, right? Imagine you go like, it is this value. What the heck should m be? You can figure out what m is. You know how fast the friggin' plane's going. That lets you know what the height is, or the double, like the width. You know, imagine like there's stuff afterwards that looks like a wingtip. If you just care about the very front of this, it's a pretty good method, right? Everything's in there. You have control over all of the terms. I think it's just pretty amazing this stuff works. Right? The idea, you just wrote down your FZ, and then you're like, well, what happened? And you end up getting like these crazy things. So some people call it airfoil theory, where people can write these down. But I will say, I certainly like to play with this stuff. And you can just write down any FZ you want. You got to take one derivative, man. One. And you just find out crazy things as long as you graph it and plot it and see what it's looking like. And then keep in mind that this needs to be on your body's surface. Very important, right? This condition lets you kind of track the boundary of this imaginary body that you have. But we're not done. I wanted to show something. I'm going to end with this sort of quick. This is just okay. So let's think about now just the speed, right? Where that was that q that I had, right? So q squared, generalized speed was what? It was w and then the complex conjugate. Okay. This I have a method. Right? So the conjugate here means I take the conjugation of the complex argument right there. Right? You could do the conjugation of this and this is the same. Any number is just the conjugate is itself. The only conjugation of the bar that you have is with the actual complex number z and then the z bar. Either way, I have a formula to really calculate what the q is, or generalized velocity, right? You know, impinging on this thing. And this will tie something together. Right? If you don't remember, right, so if z is equal to a plus ib, this is the negative of that. So they switch around, right? If z was defined by the negative, it's a positive. Thing is, like, you have the same front part, you just subtract the differences of there. So here's what's really cool. Do this out, what do you get? You get some u squared, and now you get things in terms of gamma. Yeah, so I'm just going to jump here, right? So this data is like you do this multiplication out, then convert to the polar notation. Then, is this right? Then gamma, yes, then gamma right, realize this. Right, gamma is equal to 2 pi over n. That's this. That's how you get this generalized speed, which is a function of gamma, which is a function of how far away you are from the leading edge of your body. I'm trying to spin through this. Okay, so that's just generalized speed is the thing. Okay, this is at r equal to br, right? Capital R being at the surface of this modeled blunt body. Okay, so now plug this in to that unsteady Bernoulli's equation, right? In general, I can always write the unsteady Bernoulli's equation if I have my ideal conditions. That's the point of that derivation. So you get to write that down every time. So from there, if there's no negligible pressure difference, so the z is not that big, h is small, I will then get beautiful. Okay, I just took the Bernoulli equation, neglected the gravitational term, took the difference, used this definition that this q at any speed along the surface, right? So this q represents the speed along my surface. It also does no bay, no slip. I messed that up. It's in the notes. I talk about how it doesn't no slip. But let's get to it. Let's get to it. So this is really your pressure coefficient. That's the CP. That is going to be this. Get that right? Yes. So 1 minus this thing. I didn't finish on here. So there's your pressure coefficient in the ideal case for this blunt body wing that extends infinitely behind yourself. Maybe you haven't seen that pressure coefficient before or the graph of what that looks like, but go ahead and plot it. It looks kind of strange, but you can see it seems to level off. What's more interesting is the same methodology we had for this case, except if you look at flow past a circle. Same thing. Only now I'm going to do a circle and find this pressure coefficient. The same thing. That's the cool part, right? So this F is this. A UZ plus a U radius squared over Z, where this is my radius. All right, it looks right to me. Okay, so I'll do this really quick. W here, I get a U, I get a minus U, R squared as well. Same situation. This bad boy is gamma. This would be a theta. So if I measure from the positive back, I have my actual theta, or the argument of the complex number. My gamma is just switching from the other phase. I use a gamma because I want to point towards the flow. Notice that this theta, the way everything's defined, is pointing away from the flow. So you use gamma because gamma at 0 is at the flow, right, at the very front of the body, whereas theta isn't. It's just a change of variables, but it helps for everything. Okay, stagnation. For this situation, right? What did we say stagnation was? That's going to be when that's 0. So that's going to occur at these points. X plus or minus r, y at 0. Boom and boom. So in this case, you have the situation in the ideal case. We know it's not true. We know it's not true at all, right? But you have this stagnation here and then stagnation there. I already said when you have these kinks in the lines, that's when the velocity has to be 0. So velocity stagnation points can be when the velocity goes down all the way to 0, or you can have a stagnation point where it goes from 0 and then immediately starts to accelerate. Not done. Maybe someone cares. Same thing. Convert now to this polar version. Because why? Well, if you have powers, polar is certainly easier to deal with. Boom. Use Euler's formula on this. Why am I holding up my notes all the time? Because I do this shit when I'm not looking at people and being like a hermit. I can't do this on the fly. No one can. Well, maybe some people can. I certainly can't do it. I need like time alone, being like alone, listening to sad music or something. Okay, so just expanding out just expand out this Euler's with Euler's formula. You get now this. Again, if you go back to how I defined what these potential functions were, now I know what they are. right? Now I can figure out my radial velocity in the ideal case is a u, a minus r squared, and I have a cosine for the radial part, and then the swirl part being now a negative squared, and this is my sine part. Everything coming from the definition of how I define complex potentials. So that's what they are. Not done. Let's go into my velocity on R. What would that mean? That's the speed of flow at the surface of my cylinder. Speed on that surface. So this one's not that hard because you have these ratios so things cancel out. Well, you just get this negative 2 u sine theta. Okay, and now one of my favorite moments of fluids. One of them is this. That same pressure differential, right, that same pressure coefficient was this. In this context right here, now I get it. Maybe you saw this once. But that's the pressure coefficient. That is the pressure, that is a non-dimensional pressure as I go around this sphere, right? Every point along the sphere, I track now what the non-dimensional pressure is right there. Okay? And to end, this clarifies why you maybe saw this stupid graph and was like, I guess it just does that. I don't know. So this is 1, and it bottoms out at negative 3. Here is CP, and now here's this angle. Right? And this is for the ideal case. Inviscid. That is this model function of what this graph should look like. And it looks like this. It's ideal because I have total pressure recovery. There is no losses in this flow. Clearly there's no losses. This is viscous. There's no viscous forces. Viscosity is friction of flow. So if I don't have it, I don't lose any energy to heat. So I get all my pressure and energy back. Pressure is energy normalized by volume. So in the ideal case, yes, I've lost some energy going around here, but when I get back to here, it's totally reversible. So I get it all back, baby. So this is the ideal case. It's not true. It will never be true. But it's a good approximation in some parts because you get, right, even if you do have some inviscid effects or some viscous effects right here, you'll have one that looks like this. And you get this issue of turbulence in right, in subcritical or critical flows. But like you do the same experiments. This one, right? I always get this fucking thing wrong. Boom. Yes. And the problem with this one goes like this, and it crosses. So these are sort of like, right, this is what's really happening in real life, where one of them is one of them and one of them is the other one. Okay, so this is subcritical, subturb, and this is turbulent. So if I'm laminar and have these viscous forces right here, right? This is that classic golf ball issue. If you have a totally turbulent flow over the thing, you recover more of the pressure. So this is the idea of the subturbulent regime is I'm still laminar. But most importantly, what I want to get across is if you think all this stuff is stupid and useless, in fact, I drew these wrong. I drew these so wrong. These totally look basically like this. Right? They kind of look all the same right here. So at least for some region, CP's good, baby. Can you believe that? This always bugged me where it came from. Who the heck figured that out? It has a very natural. And then like even the graph itself, like you can show how even at small angles it's cool, right? You show from here, if someone goes to you and is going like, what's that immediate pressure differential? What's the pressure at the blunt of my body for, right? What's happening at the pressure at the very tip of my body? I give you two methods using this f of z. And even in this case, by experiment, there's fancier methods. They diverge later on. But if all your boss cared about was the very front, go ahead and use this bad boy, man. It works. It works so well. Like, I mean, this is a couple. I mean, this is a couple degrees actually. You know, people like you run these codes on like things that basically look like a sphere or a cylinder at front to see, and they calculate it out and they go like, there's a pressure. But I've done these things too, and I look at like, well, I mean, the DNS like gave you kind of a good one. But everything's governed by this front pressure the body's exerting, right? At least if you're trying to figure out what the strength of the blade has to be, this is a good place to start. You can immediately say that material won't work. Just go right to it. And this always bugged me, this stupid plot that like, I've heard like some geometrical argument going like, the pressure goes past, separates. It's not good enough for me. But this really shows you how you go from the simplest case of flow. I have no losses at all in my flow. Totally inviscid, irrotational. I'm approximating this body. I know this isn't right. It can't be right. It's slipping on the surface. It's not even obeying conservation of mass. But as later we'll do like asymptotics and see that the amount of something not being right in its mathematical assumptions is something you can handle and deal with. And this works for anything, but the biggest goal, right? The biggest amazing thing is like if it is ideal, just write any fz in your head, right? Just calculate one derivative, see what the flow field looks like. No one? I think it's super cool. I was bugged by this stuff so long, but maybe no one else was. But now you can see, I just hope just this graph at least, just this part, just please focus on that. Just like, I don't know how much math that can be thrown at you. People believe like, really the analysis of the equations themselves can really tell you so much about flow before like having to, just do the tip. Look at the tip. The tip is that equation.
Take a jump off the fire escape.